Hello all, welcome to part 5 of the Buffer Overflow Primer video series. In this video, we will look at how to refine our shellcode further in order to make it useful enough to exploit a buffer overflow condition. So in the previous video, we wrote a script called exec.s in which we went ahead and called the execve syscall and spawned a shell, right? And this is the code for that. So let's try and understand what is the problem with using this shell code as is. So let's quit the program and have a look at the shell code in object dump. So if you notice, this is the shell code which we need to go ahead and plug into our buffer to exploit it. However, the problem really is that we have nulls or zeros in this shell code. And as all of us know that it is not possible to push this in as is into a character buffer array simply because in strings null would mean end of string. Because of which if we push this in as input to any program which might, let's say, be expecting a string, then the rest of the input after the null will not be accepted. Hence, we have to modify the shell code in order to remove all these nulls in some way. The second problem is that of hard-coded addresses. Let's actually load up the executable in GDB and disassemble the main program, the start routine. So if you notice, all these addresses, EBX, the /bin/bash location, right? All of these are currently hard coded. Now the problem with this is that this will not really work when we actually push this onto the stack across all computers and various different versions. So we need to set up relative addressing and not use any hard coded addresses in our shell code. So these are the main two problems. One is, we cannot have nulls in the shell code, and the solution to that is to replace all the null statements with statements which do not have nulls in them. And then is that we cannot use hard-coded addresses. Instead, we will have to set up relative addressing. So how do we go ahead and do that? Let's go back now and open up the script which we've written. So what I have done is that I have modified the previous shell code in order to accommodate both of those requests, which is no nulls in the shell code and all addressing should be relative addressing. Now let's see how we have modified it. Now what we need to do in order to set up relative addressing is go ahead and fix some point which we can use with respect to which we can go ahead and manipulate all the other addresses and locations. Now in order to do that, we go ahead and want to push some dependable address onto the stack which we can use. So what we do is, as soon as the start routine comes, we issue a jump to a label called my call statement, and this is actually going to be a short jump. And my call statement, the thing it does is goes ahead and calls another label shellcode, which is nothing but the next statement after the jump my call statement. And after the call to shellcode, we basically have a variable defined, ASCII variable defined, which is /bin/bash a 4b's and 4c's. We'll come into exactly what this is and how we will use it a bit later. So what happens? Well, as soon as the jump statement is hit, we go ahead and to this point and the call shellcode statement gets executed. Now, if you remember from the assembly primer, as soon as the call statement is issued, the next address which needs to be executed is actually stored onto the stack. So what happens is the address of shell variables, which is the beginning of this string, is actually stored onto the stack as the return address, right? Then our code transfers to shellcode. Now currently the stack, the top of the stack has the return address, which is the pointer to bin/bash and the A, B's and C's. The first statement we execute is a pop statement into ESI. What this does is it retrieves the top of the stack, which is the return address which we just pushed in, and puts it into ESI. So now ESI points to this string, right? The next statement which we actually issue is a XOR statement between EAX and EAX. And as we all know, a XOR of any quantity with itself is nothing but 0, which means right now EAX also has 0. So basically ESI is pointing to this string and EAX is 0. Let's now go back to our slides. So currently ESI points to the beginning of the string /bin/bash A, B, 4 B's and then 4 C's, right? And then 9 ESI is nothing but pointing to the A character, and 10 ESI or AESI is pointing to the beginning of the B character, and EESI is nothing but pointing to the beginning of the C character array, right? So what is the idea? If you remember Execve, let's go back to the man page. It expects 3 inputs: a pointer to the file name, a pointer to the argv array, and a pointer to the environment array, right? So what we want to do here is in this entire memory location, set up all these 3 inputs, right? So the first thing we need to do is go ahead and null terminate the name of the program. Right now /bin/bash does not have a null termination. So A needs to be replaced by a 0 to null terminate the string bin/bash. Let's go back to our code, and that is exactly what we are doing in this statement. Move byte from AL, which is nothing but 0, into 9 ESI, which is where currently A is. So what happens is bin/bash remains as is. However, the A is replaced by a 0, which is nothing but a null, right? The next statement is move the current value inside ESI into AESI, right? So AESI is this location, and the current value of ESI is nothing but a pointer to this memory location where the bin/bash string is starting. So let's say MNOP is the address of what ESI is currently pointing to. That is what is currently stored in the 4 B's, right? So the 4 B's, the placeholder is replaced by MNOP. Now finally we go ahead and move the value of EAX, which is once again 0, into EESI, which is nothing but the 4 C's we have in the end, right? So there are all zeros here. So exactly what do we have in memory right now? Well, /bin/bash terminated with a null is nothing but the file name. Now MNOP together is nothing but the address which is pointing to the file name, right? So this is a pointer to the file name itself. That is what is stored in these 4 bytes here. And then finally we have another 4 bytes, which is nothing but a null. Now if you think from a file name standpoint, we have the entire file name. If you think from the next input we require, which is an array of strings pointing to the argument, then first of all, this is the pointer to the array, which is argv, and the first 4 bytes are nothing but pointing to the file name, which would be argv0, and the next 4 bytes are pointing to argv1, which is null, right? So argv is also completed. The final input required is a pointer to the environment string array, and once again, if we go ahead and point this to EESI, which would be this entire C, then that is also a null. So what we are doing is exactly the same thing which we did in the last video, just that we want to make sure that a priori we are not inserting the nulls into this entire array. So we have written some sort of a self-modifying code which is making sure that this initial array with these placeholders A, B's and C's are now modified to go ahead and accommodate the inputs to Execve exactly. So if we go back to our code, the next thing we do is go ahead and load the value 11 into AL. Now 11 is nothing but the syscall number for Execve. And the reason we are not loading into %EAX is simply because the rest of the 3 bytes of EAX will actually be 0. And that will affect our shellcode and put zeros in the shellcode. Because of this, we've made sure that we've instead used a move byte into AL, and hence this shellcode will not be 0. Now, if you remember, what do we require for Execve when we are making a syscall? Inside EAX, we require the syscall number, which is 11, and that is what we put right now. Inside EBX, we require the first argument to Execve, which is a pointer to the file name, and that is what ESI is. And if you notice right now, we are moving that value into the EBX register, as ESI is nothing but pointing to the file name, right? The next statement is actually going to go ahead and load a pointer to argv into the ECX register, right? So if you notice right now, EBX is pointing to the beginning of the file name. Now ECX is going to point to the beginning of the array of pointers, the first of which points to the file name and the other points to null. And then this statement, load effective address EESI into EDX, is nothing but going to point to the environment pointer array, right? Which is nothing but a null right now. And then we go ahead and issue the interrupt for the syscall to execute, right? So let's run through the code again. Basically what we wanted is relative addressing to be set up. That is why we first go ahead, issue the jump statement and then a call, so that the address of where this string is stored is placed onto the stack, and so that we can use this address in our code and go ahead and do the other calculations. So once this address is on the stack, we want some way to be able to use this. That is why we pop it into the ESI register and now use the ESI register as the reference point for all other operations. Then we go ahead XOR EAX with itself to go ahead and put 0 inside it. And then we manipulate this string and change all these placeholders, the A's, the 4 B's, and the 4 C's to actually contain the null required to terminate the file name, the address of the file name itself, and then finally the null, which is going to be the second argument for argv, as well as the first argument for the environment pointer array. Once we do this, we load the appropriate registers AX, BX, and CX and DX with the arguments required for Execve to execute, and then issue the interrupt. So well, once we do this, let's go ahead and assemble this. Let's link it. Now if we actually go ahead and use object dump and look at our shellcode, starts from here, what we will notice is that there are no nulls in this shellcode. Notice there are no zeros in this entire shellcode. Right? So now we go ahead and use this shellcode in a C program to check if it is working fine. So what I've done is I've taken the shellcode from here, EB18, and then gone all the way to the final 43, right? And inserted this into the familiar C program which we used in the last couple of videos. Now let me go ahead, compile this program. and let's execute it. So if you notice, the shellcode is working and we have got our bash prompt. So well, that's all for this video. The point which I wanted to make is how you can go ahead, use a base shellcode and remove the nulls and set up relative addressing and create a much more compact and usable shellcode. So in the next video, we will look at how we will be able to inject this shellcode into the memory of a running process and make it execute it. Hopefully you've liked this video. Would request you to please leave your comments behind, and thank you all for the encouraging comments which you've already left behind. I really appreciate it, and that is what is helping me create more and more videos. Thank you.